So the last thing we really need to look at before we can finish up this first unit is just a couple of other situations that can pop up when we're trying to solve some linear systems. So what I'd like you guys to do first right now is in front of you you've got two systems to look at, one over here on the left, one over here on the right. And I just want you to try to solve each of them right now. You can use whatever method you like to try and solve it. But see what happens. Pause the video now and then we'll go through it together. So the first one here, I use substitution because that substitution is a little bit easier. So I'm going to take y equals 2 over 3x plus 1 and substitute that in the other equation. And you'll see that we quickly run into a little bit of problems here because when I make that substitution, and you probably ran into this to yourself when you were solving into it and wondering what was going on, once you try and solve for x, an interesting thing happens. When you expand this 6 through the bracket, you wind up with 4x minus 4x. And there's where you start to run into a little bit of a problem here, because all of a sudden your x's right here are going to cancel. So what we really wind up having then is that you have negative 15 over here and 0 on the right side of the equation, which makes absolutely no sense whatsoever. So the first thing, you probably thought you made a mistake first and you went through all your steps and you didn't see anything wrong. So you got to think to yourself, well, what's going on here? Why are we getting this when we try and solve this problem? So try and figure out what's going on here. Let's try and take a look at the graphs of each one. So if I try and graph y equals 2 over 3x plus 1 and 4x minus 6y minus 9, what's going to happen? Let's take a look at Desmos. So I'm going to open up Desmos here and let's see what happens. So I'm going to have y equals 2 over 3x plus 1. Okay, this looks about how you'd expect. Then we're going to have 4x minus 6y minus 9 equals 0. Sorry, 0. And here's where you see where the problem was. These two lines are actually parallel to each other. So if you were to rearrange the second line here, try and put in a slope-intercept form, you'd wind up with another line that has a slope of 2 over 3. So you've got two parallel lines, and if you're trying to think about where these lines are going to intersect, obviously they won't. So going back to our original problem here, we wind up with an equation that makes absolutely no sense. There's no way negative 15 can equal to 0. So you want to think about what's physically happening here. We have two lines that are parallel, so there actually is no solution to this problem, to this linear system. So the second one that you tried over here on the right, again, I use substitution. You may have used something different, but you wind up with something similar that doesn't seem to make a lot of sense. When I went through to solve this, I wound up with an equation that actually said that 0 equals 0. Okay, so again, when I was trying to solve, all my variables disappeared, and I was just left with something here that, again, while it is true that 0 equals 0, again, doesn't seem to make a lot of sense. How can we solve for this? So again, let's take a look at Desmos and see what happens on our graph. So opening up Desmos again, I've got our two graphs here ready to go. So let's just see what they look like here. So I've got y equals negative 3 over 4x plus 1. Okay, and then over here I'm going to try and graph 9x plus 12y equals 12, and you'll see what happens. Oh, looks like these lines completely overlap on top of each other. Okay, so if you'd rearrange this one, the second one, to slope-intercept form, you'll get the exact same equation. Y equals negative 3 over 4x plus 1. So if we're trying to think about trying to find a solution to this, well, where these two lines intersect, was a point of intersection? Well, they actually intersect everywhere each line exists. Okay, there are infinitely many points of intersection. So to summarize all this, when you're solving a linear system, there are three different possibilities you could have in terms of their number of solutions. So the first one, the one that we saw just about every single time we solved the problem up until we did this lesson, was that you'd have one solution, one unique point of intersection. For this to happen, all you need is two lines that have different slopes. The y-intercepts could be the same, so there could be something else that's the same on them, but as long as they have different slopes, they'll intersect once somewhere on the Cartesian plane. And then the last two examples we did that really illustrated the last two possibilities that could happen. So we could have two parallel lines that they have the same slope but different y-intercepts, and then they'll have no solution, they won't cross anywhere. Or you could have the case where there are infinite many solutions, where the lines have the same slope, the same y-intercept, and they overlap everywhere. So the term we use for that, we call them coincidental lines, and we say there are infinitely many solutions to this. Okay, so last thing I'm going to have you do Here are three different systems right here, and I'd like you for each one, I don't want to actually solve them, I just want you to put each one into slope-intercept form, and using that information I want you to tell me how many solutions there are, whether there's one solution, zero solutions, or infinitely many solutions to each of these systems. Okay, so give this a try, pause the video, and we'll take up the answers in a sec. Okay, so now you've given those a try, I can tell you right now this first one here, they are both going to have the same slope and the same y-intercept, so there'll be infinitely many solutions here. The second one, they're going to have different slopes, so the y-intercepts don't matter. There's only going to be one solution right here. And the last one right here, these are going to be two parallel lines of the same slope but different y-intercepts, and there will then be no solutions here. One thing that you may have been able to notice before you put them in a slope-intercept form is you look at these two equations right here. There is a multiple that exists that will let you you can multiply the first equation by to get the second equation. So if you want to multiply this one by 1.5 here, then if you do 4 times 1.5, you're going to get 6, right? So you get 6x there. 2 times 1.5 gives you 3. 6 times 1.5 gives you 9. So you can see that these two equations here are multiples of each other, which is why when you solve for y and put them in a slope-intercept form, you get the same slope and same y-intercept. Here, there's no multiple that brings one equation to the other, and you're going to get different slopes here when you put it in slope-intercept form. And over here, when you can see there's a multiple that will give you, if you multiply this by 2, that is, you're going to get from 2x to 4x, 3y to 6y, but it's not going to work here. So when you do solve, you're going to get the same slope but different y-intercept, and this might potentially be a faster way for you to see how many solutions there are instead of putting it in slope-intercept form. But if you did put everything into y equals mx plus b form, that is another perfectly good way of seeing how many solutions there are. It doesn't tell you what the solutions are, like in this case you still can't see what the POI is, but at least it tells you how many solutions there are. So that just about covers it. So just to summarize here, if there's going to be one solution, all you need to look for is that there are different slopes between the two lines. For there to be no solution, you have the same slope but different y-intercepts, and infinite solutions will have the same slope and same y-intercept. So that does it for the unit. There's a small amount of homework here. Just note here for number 3, the textbook asks you to solve it. You don't need to solve it, just predict how many solutions there are going to be. And once we have that, you can start getting ready for a test. Alright, cheers.